Welcome everyone, I'm Victor Perez, and I'm here to present you the work that we've been doing in CodePlay and in Intel for a SYCL extension on Kernel Fusion. We've been working with Luca Sama, Victor Lamula, Komuda, and Mehdi Goli. And as you know, we are in talks with people at Intel to make the extension like more API friendly and fuse it with the SYCL Graphs API. So I guess that you all know CodePlay at this point, so I will just skip this. And well, in this talk, I will first introduce you Kernel Fusion, why we need it, the benefits that it brings to the table. Then we will go through the design. I will give you more insight on how we implemented it and how it works. And then I will try to explain you what is next for Kernel Fusion and what can you build and what is the next thing that you can do with Kernel Fusion. Okay. So kernels, as you know, launching a kernel brings a bit overhead, both for synchronization and well, memory copying and all of this stuff. And in the end, we may run into situations like this in which the actual computation takes little time compared to the overhead that we get. This is, for instance, something that we run into with short-running kernels, like in DNN or in other kind of math-heavy libraries. So our motivation here is to get rid of this overhead, right? And by fusing the kernels together. And that way, we could launch n kernels in a single one. This, of course, we are proposing this to do this at a compiler level, but this could be done manually. However, we think that the manual approach, first of all, it will require way much work. You will need to write the kernels yourselves. You could make mistakes. People make mistakes. We are programmers. We all know that we make mistakes. And it would require domain-specific knowledge, and even it would require changing code that maybe we don't have access to. So in the end, we think that the only feasible solution is doing this at the language level. So now let's go through the extension that we propose. Okay, the base idea of our extension is that the user should be in a driving seat here, right? So it's a user-driven extension, and we are proposing an easy-to-use API so that we don't need to do a lot of changes to the code. The changes to the setting code base should be minimal to make the adoption easier. Okay, the user is at the driving seat, but in the end, the decision whether to fuse or not should be made by the runtime in an implementation-specific manner to ensure optimization, because that's what we want to get, optimization. But even most important, that the resulting kernel is going to be functionally equivalent to the originals. So this is basically what we are bringing to the table. The only thing is that you usually will have to do when implementing kernel fusion, when introducing kernel fusion to the code base, will be passing a new property to the queue when creating the queue. That's quite simple. And before submitting the kernels, you just put the fusion in kernel mode, submit the kernels as usual, not a single change to the code here, and then call complete fusion. And in the moment that you complete fusion, then the kernels would be fused together and scheduled as usual. But okay, I'm talking a lot about just reducing the overhead, but is it worth it? Is it worth all of this work, like implement a new API just to reduce overhead a bit when we already have SYCL graphs? That's where that's what other optimizations that we are performing come into play. For instance, data flow internalization. Okay, so this is the usual data flow that we get when submitting this kind of kernels. We have a kernel reading from global memory, writes results to global memory again, and subsequent kernels will read from these buffers. We have some overhead here due to the need of writing and reading to global memory. With our extension, what do we get? Exactly the same. We are not for now, we are not improving anything. However, the kernel fusion extension is capable of inferring that two accessors refer to the same region of memory. So at least we know that this buffer that we're accessing is the same. Okay, this is an improvement. This is where data flow internalization comes into play. Through a user-driven extension, we can mark a buffer or an accessor as private or local accessible, so that we don't need to write and read the results back and into memory all the time. So that way the memory accesses will be internalized. Okay, just using these two properties that you can pass to accessors or buffers constructors, we can express local or private internalization. Local meaning that only work items in the same workgroup will access this region of memory and the same region of memory, and private meaning that a given region of memory will only be accessed by a single work item. Okay, and why do we need a property? This should be automatic, right? Well, it's kind of tricky because in some cases, well, for instance, here we have a buffer. We think that we should internalize the buffer, right? Because we can, why not? It's an optimization. But by internalizing the buffer, what we get is that the results will not be written back to memory, right? So subsequent kernels outside of the fusion process that try to access this buffer will get just garbage, right? That's why this is user-driven. The user should just mark the buffer as internalizable, so that the runtime can perform these kind of optimizations and make sure that the user will not be using the results afterwards. Okay, now I will give you a small insight in how we implemented all of this. Okay, well, I will give you just, I guess all you know how the runtime works and how kernel submission works, but basically the main change that we introduced here is that now when you submit kernels to a queue, you are not sending them to the scheduler. Well, you are, but the scheduler is not scheduling them right away. It is storing them and all of the needed information into a fusion list. We call it a fusion list because it has a cool name, but it's just a list of kernels. Okay. Then when the user calls complete fusion, the fuser, which is implementation defined, will gather this list of kernels and it will fuse them together. In our case, we are using a JIT compiler for this. So we only support SPIRV for now, although we are improving in this aspect. And basically the fuser gathers all of the needed information, like of course the code of the kernels to fuse, the constants that are being used in the kernel, whether the list of identical accessors, and of course the list of accessors that you can internalize, and passes them to the JIT compiler. The JIT compiler then fuses them together, internalizes the buffers or the pointers, and performs contact propagation, another kind of crazy optimization, right? And just the result of this is translated back to SPIRV or to whatever representation and sent to the scheduler as usual and submitted for execution as usual. So this whole process is transparent to the user. And what does it look like in the code? Okay, so when a user calls complete fusion, the JIT compiler will be something like this, right? We just call the first kernel. In this case, we are fusing two kernels, then inserts a workgroup barrier here and calls the second kernel. Why the workgroup barrier? Well, as you know, in SYCL there are not the byte-wide barriers, but in order to get some kind of synchronization, at least between both kernels, that's the best that we can do. If the users knows that they need no barrier, they can just pass a property and we will get rid of the barrier. That might give some better performance, and we'll be able, the JIT compiler will be able to perform further optimizations. Yeah, so omitting the barriers. Okay, as I said, the runtime is capable of identifying identical accessors here. So it reduces the number of arguments being passed, removing the identical accessors, no longer needed. Okay, we also perform constant propagation here. We have that information at runtime. We can use it, why not? So we just use that information, and basically scalar arguments, we get rid of them and just use the constant information as a pass in the pass, something like that. And finally, as a last step, we inline the fuse kernel functions, perform generalization, and then run all of the optimizations that we can run in order to get the final result. Okay, performance evaluation. The numbers that we are giving here, they belong to the compute CPP implementation, not to the new DPCS+ implementation, and we basically use the system for evaluation. The first case study is SYCL-DNN. SYCL-DNN is a library, deep neural network library implemented in CodePlay, and we are using two kinds of benchmarks here: micro benchmarks, so sequences that we took from actual models, and they are arithmetic heavy, and they are sequences that we analyze that we can fuse together. So, for instance, batch normalization and ReLU nodes. And also we have benchmarks for full neural networks runs. The macro benchmarks, when running them, we got pretty good results, especially on CPU. We got like all of the benchmarks got an up and speed up in CPU, and more than 50% got a 1.78 speed up. On the GPU, the results were also quite good, reaching a 2.36 speed up. So I think the results were quite good in the micro benchmarks perspective. And when running the full neural networks, yeah, they weren't that good for the CPU. In fact, as you see, you see that we are running ResNet 50 and VGG16 networks here, and we did a little trick here. We added 2 additional runs. We modified these neural networks so that they would use a less optimized but more efficient-friendly algorithm for convolution, and there we were getting better results on the CPU. On the GPU, however, in the GPU the thing changed quite a bit. So just by performing kernel fusion, you don't have to look at the trick at the less optimal results. Just look at ResNet 50 and VGG16. Just by changing 3 lines of code, basically we are getting 35% improvement in VGG16. That's quite good. Why are we getting these results? Well, we analyzed them and we saw that only reducing the overhead of launching kernels in such a kernel heavy, like you are launching a lot of kernels in VGG16, that led to a 35% optimization in the GPU. Okay, for SYCL bench, we also run SYCL bench test here. This is outdated, okay, but this is the numbers that we got back in the day. I don't know if I can give you the new numbers, but I won't, just in case. Okay, so out of the 9 benchmarks that use more than 1 kernel in Polybench, we can fuse 6 of them, and we can perform internalization only to 2 of them. Well, that's what we get. On CPU, the numbers were not that good. We can perform internalization in correlation and covariance benchmarks, but we found that we were not getting good results. Why? Well, mainly because the correlation and covariance benchmarks have like half of the code is linear, the other half is quadratic, and we could only optimize the linear part. So it's simple. We could not get that good results in CPU. But again, on the GPU, things change a bit also, especially on Gram-Schmidt. The Gram-Schmidt benchmark, that we got really good numbers there, because it's a benchmark which launches a huge amount of kernels, a huge amount of kernels, and just reducing significantly the number of kernels that we launch led to almost 3.5 improvement. That is really good. Okay, and now I will give you an update on what is going on with Kernel Fusion right now. Well, you can already use Kernel Fusion, not the Compute CPP original version, but the DPC++ new one. The API is slightly different, but if you have followed this presentation, you will be able to use it, no problem. Again, the proposal is open here. It's already been merged. You can visit it. You can check it out. It's open. And the next step is to align this proposal with SYCL graphs. So SYCL graphs already introduces an API to group kernels together. So why should we duplicate this? We should keep it simple, right? And that's why we are proposing the Graph Fusion API to align with our Intel and Coldplay colleagues. So again, why Graph Fusion? We would simplify things. We would unify two similar APIs, and also something that graphs introduce, we will be able to reuse fused kernels. Right now, the solution that we give to this, of course, you cannot reuse fused kernels, but at least kernels are cached by our implementation, so you don't get the JIT compiling overhead all the time. But being able to just reuse the fused kernels with SYCL graphs, we think that that is a way better solution. Okay, and what are the changes? Okay, on the left you have the original version of the API, and on the right you have the changes that you would need to use Graph Fusions. Given, I mean, if you already use SYCL graphs, just a line of code, that's it. So if you already use SYCL graphs, you would build the graph however you want in the two ways that my colleague introduced, and then when finalizing the graph, you would only need to pass this perform fusion property, and that's it. You would get the benefits of SYCL graphs and of SYCL kernel fusion. In conclusion, kernel fusion can improve the performance of SYCL applications, especially when you run into these workflows of short-running kernels. The extension allows users to fuse SYCL kernels at runtime. This is already a stream in DPC++, so you can already use it, you can already test it, try it, try to break it, and get new numbers. And again, the future for this is this is an experimental application, so experimental extension, so you should not use it in production code, and it won't live for longer, for too longer, because we are going to align with SYCL graphs. Here you have all the links, take pictures. We presented this extension in TACO last year, and yeah, so that's it. Ask me anything. Any questions?
Thanks, very interesting. So maybe can you comment on how the kernel configuration in terms of the ND range would affect the ability to fuse, or how you handle that?
Yes, of course. Well, our original approach was that we would only be able to fuse what we call homogeneous ND ranges, but we found out that that's not needed. I mean, even with heterogeneous ND ranges, you can perform fusion by modifying the source code. So, for instance, introducing guards so that no more work would be performed, right? And also, you would need to do array mapping. Right now, we can fuse and we fuse kernels basically with the same number of workgroups, and it can be configured in whichever topology. I mean, you can have 3D kernels, 2D kernels, as long as the number of workgroups is the same, we can do that. And also kernels with different number of work items, introducing these guards. What issue did we find, and why don't we allow to fuse any crazy combination? In order to preserve semantics, in some cases, you will need to launch more work items than originally intended. So that's what we don't do. in the moment that you would need more work items, given this remapping, I mean, explaining it here would be a bit too much. I think that I pushed a design document for that. Yeah, I think I did. So you can check it out in the D++ repo.
Yeah, loop fusion is one of the hardest problem in compilation. So I'm not sure I've understood the API. So is the API an order to do loop fusion or kernel fusion? Or it just say, oh, try hard whether you can fuse the kernels if you, so.
Okay, so if I got your question, you don't understand the intent of the API or the semantics?
No, I intend
okay.
I used to have a PhD student doing
okay.
a loop kernel fusion. But the problem here is that are you at runtime, you try to figure out which kernel you can fuse with some try and error, or
no, the thing is that it's user driven. So the user
it's a user promise that for some hypothesis that he probably doesn't know what you can do, but he say, oh, probably this implementation can do loop fusion, or with
it's I mean users that know the kernels that they are running, they know whether you can fuse them or not, right? And
yeah, but it's only you know your implementation. The user doesn't know what how it will be compiled actually, these kernels on your architecture.
Oh, what the Git compiler does. Yeah, I mean that's
it's a kind of zero knowledge communication between the user who wants to fuse but doesn't really know what your compiler can actually do and how it is compiled on the final architecture. So that's why.
Yeah, I mean the user can. It's a user hint in the end, so the user can hint whether it can hint whether he wants to or she wants to fuse a given set of kernels. It can hint whether he wants or she wants to internalize some memory accesses. So it's all a hint. The runtime and the Git compiler should be able to infer whether this fusion is profitable or not. We are building more tools. We have a poster. I don't know if you saw it, the MLIR poster. And with further analysis and host and device code analysis, maybe we can infer whether fusion is profitable and legal. So yes, in the end, I think that also the average user doesn't know what a compiler does anyway. So I mean, yes, of course. I always say that, and I think that this is true. Optimization should be tested. So it's a bit of trial and error in this case. I spent a lot of time writing tests and benchmarks, and in the end, I found out that code that looked like feasible wasn't feasible in the end, and code that I thought that would get great performance didn't, and the other way around. So just I would say this today. So just test, and if you get better performance, just do it.
So just follow-up question. I guess so the developer has to know exactly which layer, which operation can fuse with the next one, right? So developer has to define that function, define that API, so that the runtime can fuse. So I don't know if you ever look at the compiler stacks like TVM. They can do some graph level automatic fusion actually. So that's actually my poster talk about that, because we have few layers that can be automatically fused without developer's knowledge. So I think that's something maybe SYCL can, in future can be supported by TVM, which can make it more automatic. That's my one comment. The other thing is I'm curious about this performance gain, like which layer, when you talk about the machine learning network, which layers are benefit most from this fusion? Is that like a memory bound, like ReLU, softmax, all this kind of what layers are giving the most gain?
Yes. So the thing is that kernel fusion allows both fusion in the layer, right? So if you have a layer implemented with n kernels, you can fuse some of them together. And the VGG16 results, we were mainly fusing the convolution kernels that, well, maybe Dina knows better, but it's implemented with several kernels, and that was giving great results. And then in other benchmarks that I'm not showing here, that we have performed lately, we are fusing. I mean, you know that these kind of frameworks have what they call graph optimizations, right? So we implemented these graph optimizations with kernel fusion. Instead of rewriting a new kernel implementing the graph fusion, we just called the function implementing this node, called the function implementing this other node, and we also got some performance improvement that way. So for this kind of scenario in which you have to perform graph optimizations and graph fusion optimizations, I think that having this aid to the user, like that, instead of having to rewrite the code, you can just call start fusion and complete fusion, or build it with SYCL graphs and pass this additional property. I think it's a good improvement. I don't know if this answers your question, but okay.
Question in the back.
Can you give us example of where you should not do fusion?
Okay. Yes, that's it. I only have 30 minutes. We learned a lot about these kind of scenarios. Okay, the main blocker is when fusion is not legal, is when you would result in race condition because of fusion, right? So basically, what I did when writing these benchmarks was, okay, I see the memory access pattern of this kernel. I see the memory access pattern of this kernel, how accessors are used, and if they match, or if you don't get overlap, like you wouldn't result in race conditions because of fusion, I would just fuse the kernels together, and that's basically what a user would do in the end. He has to know, or she has to know the memory access pattern of each kernel, but as long as you know that little information, you can ensure that that two kernels can be fused. And again, the very next step, and in the future, maybe the runtime or the JIT compiler should be able to say, okay, you cannot fuse these two kernels because you would run into a race condition, right? So maybe with further static analysis, you can infer this kind of information, and you can again help the user, because in the end, all of this is to help the user to write more efficient and safe code.
Any more questions? Yeah, I think we've got. Sorry, this one was first. We'll come to you.
Just a quick follow-up to the previous question and the question there. So it's not like a hint then. So is it more like a promise from the user to the implementation that, okay, this is allowed, and the user can generate really broken application if he accidentally uses the attribute?
It is indeed a hint, right? It is a hint. And then it is implementation defined whether your implementation is more intelligent or not, whether to trust the user or not, right? So if you have a good implementation, right now we are in the early stages, so we are not doing that. But if, just imagine that you give this hint to the runtime, and the runtime is capable of saying, okay, I'm gonna fuse these kernels together because it will give good performance and it will be safe. Okay, it will do it. And just imagine that the kernel can also infer that fusion would not be safe, or would result in a non-functional equivalent code. Then the JIT compiler would not perform fusion. And even the next step, this is like the very next step, would be that the JIT compiler knows that the resulting code would be equivalent, but it wouldn't be more efficient. Then it wouldn't perform fusion, right? So it is a hint, and then it's implementation defined whether you have a good system or a less good system that you can trust the user more or less.
Final question at the front.
Can you fuse like multiple fused kernels together? So could you say fuse these two kernels, and then fuse those fusions together?
No, you cannot with the current API because in the end, in the moment that you call complete fusion, you are fusing the kernel and submitting it, and that's lost. Maybe in the future, I don't know whether SYCL graphs people, but maybe you will be able to with SYCL graphs. I don't know. What do you think?
I think you'll all be able to have a fused executable graph, then add it as a node and a graph that you then call complete fusion on again. So I think actually potentially you could, whether it would actually work or not, I don't know, but theoretically.
I mean, it should, right?
Okay, I think in the interest of time, we'll leave it there. Thanks for the presentation. Thank you, speaker.
Thank you.